Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we're going to solve 3 moves. This prompt states, write a function that calculates the total number of ways to reach the last spot on a board using any combination of 1, 2, or 3 jumps. So let's see what this means. As an example, let's take a board of length 4. We have the starting spot here, and we want to calculate the total number of ways we can combine 1, 2, or 3 jumps to reach the end of the board. So we can go 1, 2, or 3 spots at a time. So from the starting point, we could go 1, 1, 1, 1, 3, 1, 2, 2, 2, 1, 1. All these are different possibilities to reach this last spot. So if we wanted to count the total number of possibilities using a combination of 1, 2, or 3, we see here they are, and this is 7 total possibilities to reach the last space on a board with 4 spots. The one constraint we're given is that if the board is length 0 or length 1, you assume it's one total move in both cases. So there's not necessarily a right answer to this when you have these really small boards. A board of length 0 doesn't really have meaning. So this is actually done as a favor by the interviewer. It just simplifies the problem and allows you to focus on the logic instead of worrying about edge cases that may arise. So just know, if you ever have a board of length 0, it's going to require one move to place your piece. So let's first look at a few simple cases to gain some intuition. With a board of length 1, it's going to take one move. There's only one possible answer. With a board of length 2, there are 2 possible ways to reach the final spot. We can go 1, 1, or just 2. For a board of length 3, there are 4 total moves that could get us to the end. 1, 1, 1, 1, 2, 2, 1, or just 3. Then we already saw a board of length 4, and it took 7. Then once you move to 5, it starts to grow even more quickly. So this very quickly starts to become too difficult to calculate by hand. There are just too many cases that we need to think through with this bottom-up approach that we've been using. So instead, to gain some more intuition, let's think about it from the top down. Let's imagine there are 100 spots. Well, to reach the last spot, space 100, there are only 3 spaces that we can reach the final spot from. Since we can only make 3 moves, we can get to the final spot from space 99, 98, and 97. So then really, we don't have to calculate all the ways to get to the final spot. We just need to know all the ways to get to the 3 spots before it. If we have the number of ways to get to 99, 98, and 97, we can easily calculate 100. Then to just get to 99, 98, and 97, we only need to know the 3 spots before them. We can figure out how to get to these final 3 spots that will lead us to the end. So we can clearly see we have some sub-problems forming. We know to get to the end, we only need to know the final 3 spots, but then to get to these spots, we only need to know the 3 spots before them, and if we continue to calculate the total moves to get to each spot, we would eventually reach the bottom or the starting point to the board. So we haven't thought through it yet, but we can see this top-down approach forming, where all we have to do is calculate the 3 spots prior to any one to get the total moves to reach it. So let's go back to the original example and see if we can form the logic to create this top-down solution to solve the problem. So if we want to reach the final spot, space 4, we know that we only need to calculate the number of moves that it takes to get to the prior 3 spots. So spot 1, spot 2, and spot 3. And we saw in the simple cases, we can get to spot 1 in 1 move, spot 2 in 2 moves, and spot 3 in 4 moves. And then to get to the final spot, it's 3 moves from the first spot, 2 moves from the second spot, and 1 move from the third spot. So if we include those in the number of ways to reach each location, 3 from the first, 2 from the second, and 1 from the third. And we see now, these are all the total possible ways to reach the fourth spot. So we can simply sum together the number of ways to reach the first spot, second spot, or third spot. In the case of a board length 4, or for an arbitrarily large board, we just sum together the number of ways to reach 1 spot back, 2 spots back, and 3 spots back from the end. This will give us the solution. And one thing I want to quickly note is you might be thinking, if I'm at spot 1, I can also go to spot 2 and 3. And these are already accounted for in the number of ways to get to that spot. So going 1, 1 is one way to get to spot 2. So it's already accounted for. And then the same with spot 3. So we're already accounting for these ways to get to the prior 3 spots. So we just sum together the total number of ways to reach each of the prior 3 spots, which is going to be the solution to get to the final spot. So now, let's quickly walk through and summarize the logic that we've discussed. You can find the total moves to reach any spot on the board by summing the total moves to reach the 3 spots prior. So if we want to find the total moves to reach the board length, which is the solution, we sum the total moves to reach this spot, and this spot. However, to find the total moves to reach each of these 3 spots, we need to find the sum of the 3 spots before them. So to find the total moves to reach this location, it's the total moves to reach this item, plus this item, plus this item. Then the total moves to reach here is this item, plus this item, plus this item. So we have this repeating subproblem that we need to solve. We keep finding the total ways to reach each spot with smaller and smaller input. So we're recursively calling it with a smaller board length each time until we reach the base case. Once we reach the base case, we return constants and then can start solving each problem locally. We can find the number of ways to reach this location, and so on, and we keep summing them up and combining the answers to each of these subproblems until we get back to the original function invocation, and then we have calculated the total moves to reach each of these spots. So then we solve for this board length, and then once we solve all these subproblems and then the final subproblem, we will have calculated the overall solution and know the answer globally. And now let's view this as a recursive subtree. We can find the total number of moves to reach the 6th spot by summing the total number of moves to reach the 5th spot, 4th spot, and 3rd spot. But then, to find the total number of moves to reach each of these spots, we then just sum the 3 spots before them. And we do this and branch and create these recursive cases until we reach the base case, and then we begin returning constants, and then can solve each of the subproblems, and then return those values up to the functions that called them until we get back to the original call, and then can use these values to calculate the solution. So the code for a naive brute force solution looks like this. We have the base cases, where we have a board length of less than 0, returns 0, or when we reach 0, it returns 1. Otherwise, we just keep calling the function recursively by summing the number of moves to reach each of the 3 spots prior. So we find the number of moves to reach these smaller board lengths or these sub-board lengths for the subproblems, and then combine them to get the solution. And let's quickly look at the base case. We keep calling these down until we reach the base case, which returns constants. When we get to 1, we subtract 1, 2, and 3 for the 3 spots prior. 1 minus 1 is 0, which returns 1, and then -1 and -2 return 0. So the number of ways to reach 1 is 1. Then at 2, we have the answer to this subproblem, and then 2 base cases. When we subtract 2, it's 0, so we return 1. And then when we subtract 3, it's -1, and we return 0. So we have 1 plus 1 is 2. And then we've already seen the answer to 1 is 1, and 3 minus 3 is another base case, which is 0 and returns 1. So we have 1 plus 1 plus 2 is 4. And we already know this is the number of moves for a board length of 3. And you may recognize that we're doing a lot of repeated work. To calculate the total moves to reach the spot 100, we need spot 99, 98, and 97. But then to reach 99, we need 98, 97, and 96. Then to reach 98, we need 97, 96, and 95. So we see the same subproblem appearing many times. For example, we see 98 here, 97 in all 3 of these spots, and then 96 here. So not only do we have subproblems, we have overlapping subproblems, and this means we can use dynamic programming with memoization to optimize the solution. By doing this, anytime we see the same subproblem, or this count total moves function being called with the same value, this means we can use the memoized version and return immediately. So let's again take a look at the recursive tree. To calculate the total moves to reach 6, we need the total moves to reach 5, 4, and 3. But then we see this branching and these overlapping subproblems. We need 4 again, we need to calculate 3, and we see 3 used multiple times, 2 is used multiple times, and so on. So we need the same values many times to calculate the solution. So these white circles represent the first time we calculate a value for a given subproblem, and then after we calculate it, we memoize it and can use this value and return immediately anytime we see this subproblem occurring again. So what we do is we remove all this work required by the overlapping subproblems. So not only can we return immediately, we also remove the need to go deeper into the tree and remove everything below that first memoized return after we calculate it for the first time. So with dynamic programming, this optimization allows us to get down to an O of n linear time solution, which is much, much better than the O of the 3 raised to the n solution in the brute force manner. So by incurring an O of n space, we greatly improve the solution to this and remove the need to calculate all these overlapping subproblems by memoizing the solution to subproblems and allowing us to return immediately anytime we see the need for that solution again. So then, an optimized solution to this question will take the brute force recursive solution and introduce a memoization array where for each input board length, we store the number of moves for that board length and then can use it and call on it instead of always performing these recursive calls. So now let's just quickly talk through the steps of the solution. We're going to recursively find the total moves to reach any spot by summing the total moves to reach each of the 3 spots before it on the board. Once we reach the base case, we return constants and can start building up the solution by finding the answer to the subproblems and then passing these values along, finding each solution locally until we reach the end and have the global solution. We realized we had overlapping subproblems, and we're going to use memoization to remove the duplicate work and prevent the need from entering the recursive case. This is the top-down dynamic programming solution and an optimized solution for this problem over the brute force solution. The big O complexity is linear time and linear space. We touch each spot once or each board length once from the base case up to the board length, and we memoize the values so we don't spawn additional recursive cases. so we handle each sublength only once and combine the solutions to get the global solution. We use recursion, which requires n items, or O of n space, and we also use O of n space for the memoization array. And now we're ready to implement the solution function countTotalMoves. First, we just initialize a constant to represent the uncounted spots, and we set this to -1. We fill the memoization array with this value, and then when we see a -1, we know we haven't calculated the answer to that spot, and then recursively calculate it and then replace it with the actual value. Since the board itself is a 1D array, so we're going to use an array to memoize the total number of moves to reach each spot on the board. And we just initialize the value for each spot as -1. Since we're going to be using memoization, we're going to need to pass the memo data structure to the recursive function. So let's write a recursive helper called countTotalMoves memoized. So we initialize the recursive helper function. We're going to handle the first base case, where the board length is less than 0. This means it's an invalid board, so we simply return 0 because there are no possible moves. For the second base case, we check if the board length is 0, and we saw from the constraint that we're going to assume a board length of 0. We'll always return 1. And then the final case is if the board length has a memoized value, or it's not equal to an uncounted spot. If this is the case, we can return the memoized value for this location. If we don't hit any base cases, or we don't have the value memoized for the current spot, this means it's the first time calculating the value for this current board length, or the current spot that we're at in the recursive call. So to do that, we calculate the total moves for the 3 spots before it recursively. Then we immediately memoize the value for this spot. And then we return the value for the spot we just calculated. And that's the recursive function. This calculates the total moves for the entire board. Then once we calculate the total moves, we return it from the main function. So in this question, we realized to calculate the total moves to reach the final spot with a combination of 1, 2, and 3 jumps, we could just calculate the total moves to reach any spot on the board, and then we could sum the 3 spots before any given spot to calculate its value. So we solved these subproblems, combined the answers, and were able to calculate the solution. However, we recognized that the subproblems were overlapping, so this was a great time to use dynamic programming and memoization to improve the time complexity and come up with an optimal solution. Thanks everyone, and I'll see you in the next lesson.